So we're going to look at unit tangent and unit normal vectors. But before I do that, I want to show you a really cool beans picture. And so to kind of reinforce what we've been doing so far. So I hope you can see my screen. It's got a curve on there. Can you see that curve? It's kind of light. It's got a lot of loopy loops in there, and I'm going to hit play. And the point of this is I want you to notice there's a vector that's moving around on this curve. And what it's doing is that's the velocity vector. Notice how it's always tangent to the curve, no matter where it's located on the curve. Now it's coming backwards. Yeah, it's pointing in the direction of the orientation. But so that unit tangent vector, or not unit, just a regular tangent vector, is the r prime of t. So if the curve itself, which we call the position vector, is given by r of t, a nice vector valued function, r prime of t, the derivative, is always going to give you a vector that is tangent to the curve at any point. And so it's kind of moving around here, and that vector is the velocity vector. Pretty cool, huh? Are you guys excited? Okay, maybe not. All right. We'll look at some more of that in a moment. So let's define the tangent and the normal and the binormal vectors in this section. So let's take a look here. So we're going to, I don't know why this is not working. Oh, interesting. So we're going to first define why we're looking at all this. And the reason why is because we want to use some more of those physics applications of motion. So in the past, we've had the derivative of a function was the slope of the tangent line. With vector functions, we get that same result with one exception. So you get this r prime, which is the tangent vector, provided it exists and it's not the zero vector. Okay, so the tangent line to r of t, and r of t gives you the curve, that's the position vector, at a point P. Then the line that passes through that point P is going to have a direction vector that is r prime. So that's really kind of cool. That's what's exciting. Okay, and we really do need to require that r prime isn't the zero vector in order to have a tangent vector, of course. Well, when is r prime equal to 0? If your curve has a sharp corner or a cusp. A lot of times that's when your r prime is either going to be 0 or undefined. So you need that, otherwise you'll not have a direction for your nice little tangent vector. Okay. So as long as your r prime isn't the zero vector, everything's cool. And now we can define the unit tangent vector. And here it is, big definition here. If C is a smooth curve represented by r, that's the vector valued function r of t, also known as the position function, aka position function. Okay. The unit tangent vector, which they denote with big T of t, that's important, at time t is defined as this. So here's what it is. It's just the unitized derivative. That's all it is. You find r prime, and you all know how to do that because that's a previous section. And then you unitize it. How? You divide by its magnitude. Voila. And that's why they call it the unit tangent vector. Now, sometimes getting the unit tangent vector can be a little bit messy, calculus-wise and algebra-wise. But there's times you're going to need this unit tangent vector instead of just the tangent vector. So there are going to be times in this semester where we're going to want to unitize that velocity vector to get big T. Okay, and you'll see that more and more when we get into the vector calculus module of this course. Okay, let's do an example. Easy peasy. In fact, it's so easy, we're going to just do it in 2D, but you can do it in 3D for later. So here's a curve, also known as a position function, also a vector valued function, and they graphed it for us. Since it's 2D, you can use your graphing calculator in parametric mode, And it's just a parabola opening upward and oriented going from left to right, okay? And they want us to find the unit tangent vector. Well, what they're telling us is go get big T. That's all. And then after we do get him, we'll evaluate him at time t equals 1 second. Okay? Easy peasy, easy enough. Okay, so the first step that you do when somebody asks you for big T is you go get R prime. And then the second step is you unitize it in that order. So that's all. It's not that hard. Show my erase tool. So R prime is equal to a vector. I'll put my little brackets in there. And so I'm just going to take the derivative of the components for R prime, and my erase tool is, sorry, acting up. Okay, so the derivative of t is 1, and the derivative of t squared is 2t. Fine. Now what? Go ahead and start getting the magnitude of this velocity vector. Remember, that's the same as speed. Speed is the magnitude of velocity. And so you're going to go, okay, I'm going to get the square root of the sum of the squares of the velocity. And then I'm just going to get square root of 1 plus 4t squared. Okay, that's speed, essentially. Notice that speed is a scalar function. It's not a vector. And notice it is a function of time. So now we can put this all together. And of course, I didn't give myself enough room because I never do. So let's finish it down here. Big T, which is defined as R prime divided by its magnitude. We have the vector 1, 2t divided by the square root of 1 plus 4t squared. I don't let you leave it like that to get full credit. Please distribute the scalar. So the final answer for big T is a vector that has these components: 1 over square root of 1 plus 4t squared. And then the other component is 2t divided by square root of 1 plus 4t squared. Yay! And there's your big T. Now they did want us to go one extra step for this problem. And they wanted us to evaluate it when time t equals 1 second. Easy enough. You're just going to do a substitution, and you'll substitute time t equals 1 second. All right. I'm just going to do that here. Substitute it in there. And I get the unit tangent vector at the point when time t is 1 second has 1 over square root of 5 and 2 over square root of 5 as the components. And they did a little graph for you here. When time t equals 1, so if you plug t equals 1 into your position vector, so you get the point at which you have this tangent. So the 0.11, and they did show us there, so that's the position, and at that position, this little unit tangent vector. Now, when I graph vectors, I always graph it in standard position first. So you would, you would find 1 over square root of 5, 2 over square root of 5, like that, and then you translate it or move him so that that unit vector is, he has his initial point starting at the point that he's associated with. So we just move him, maintaining his integrity, which means direction and magnitude. Okay, and that's it for that example. Now we'll fill in the blank. The tangent line to a curve at a point. So the tangent line now, not the tangent vector. So if I draw a tangent line to this point, here's a tangent line to a curve at a point, is the line that passes through the point and is parallel to the unit tangent vector. Yeah, they're parallel. In fact, you can, if you had to come up with parametric equations, you could just use that tangent vector as the direction vector for your line. So I'm going to do another example of a 3D curve that we'll get the unit tangent vector for. So now we're going to jack it up to 3D. And this vector valued function, if you graph it, is a helix. And helix curves are kind of cool because they, they look like a little squiggly there. So that's what this is a portion of right here. It's kind of like a portion of the squiggle. And they want us to evaluate the unit tangent vector when time t is pi/4 seconds. Fine, but we got to go get the unit tangent vector. So I'm just going to first go ahead. So step 1 here, for example 2, go get r prime and then unitize it. Okay, so here we are with example 2, r prime, and I'm going to write it in component form. So the derivative of 2 cos is -2 sine. The derivative of 2 sine is 2 cos, and the derivative of t is 1. Fine. Then go unitize it. And in order to unitize it, I'm going to first go get that magnitude. So I'm going to take the square root of the sum of the squares of the components. And you want to simplify this as much as you can. And that doesn't mean you get to do anything algebraically incorrect. Like, do not distribute this radical over the sum. What I do want you to do to simplify is notice the first 2 terms under the radical have a common factor. So the last term does not. He's still +1 out there. But there is a trig identity that says sine squared plus cos squared is equal to what?
1.
So we really have the square root of 4 plus 1, which is square root of 5. And now you're able to put this whole thing together. So over here, your t of t is going to be your r prime divided by magnitude of r prime. So that's going to be this vector here. -2 sine t to cos t 1, and divide that by the magnitude, which is square root of 5. And then go ahead and distribute that scalar of, division by square root of 5, just to make it look pretty. And voila, there is your unit tangent vector written as a function of time. But now that to finish this out, they did want us to evaluate our t of t at the point when t is pi/4. No problem. So now you're just going to substitute pi/4, and then you'll get a nice constant vector. And you have to do a little bit of trig here because you have to know what the sine and cosine of pi/4 is. Yeah. And I think it's square root of 2 over 2 for both. And then after cleaning it up a little bit and reducing, I claim that you'll have a lot of 2's cancel. So the first component after canceling will be negative square root of 2 over square root of 5, which if you can leave it like that. I don't care. If you want to impress me, that actually can be written equivalently as negative the square root of 2/5, but I don't care. And the second component is square root of 2 over square root of 5, which is also the square root of 2/5. And finally, 1 over square root of 5. Okay? And that is the unit tangent vector evaluated when time t is pi/4. And they show a little picture of everything that's going on here. You've got the curve. You've got little, your tangent vector that we just did would be tangent to the point. Tangent to the on the curve. And if they did draw a tangent line and you had to come up with parametric equations, sure you could. Okay. And we're not going to do that part of it. We're just going to move on. So we're done talking about big T of t for now. So what I wanted to show you, let's see if I have it, is I wanted to show you a 3D curve here that's kind of cool. This doesn't involve the unit tangent vector, but it's kind of last lecture. Here's a curve in space. That's that white curve. And you see 2 vectors there to the curve. One of them's tangent and the other one isn't. And it turns out that the one that's tangent represents the velocity vector, and the other one is the acceleration vector at that point. The acceleration vector is not tangent. It could be anything. Okay, so if I hit play here, let's see what happens. Whoa, check out. So the blue is the tangent vector. That would be the velocity vector. And the red is the acceleration vector. Sometimes they're orthogonal, like at different points, but most of the time it looks like the velocity and acceleration vectors are not orthogonal. Ooh, isn't that kind of pretty?
Is the acceleration vector fluctuating like left to right, or is it rotating each time?
It's doing both. And it's always going to point in the direction that the curve is turning. We'll see that in a little bit. Pretty cool. All right. I just wanted you to see the ideas that we're covering in this chapter. It's really important. And so if you see it visually, it kind of helps. Or at least I hope it helps. Okay, let's talk about the next big vector. So now you know what big T is. All it is the unitized velocity vector. Okay, what else? Well, we want to get a very special vector next. We're going to call it big N. And big N, we have some requirements. We want big N to always be orthogonal to the big T. Okay, that's our wish. Now, don't say the unitized acceleration vector, because that won't work. As you just saw by that last little diagram and animation, the acceleration vector, sometimes you get lucky and it might be orthogonal to the velocity vector, the tangent vector, but it looks like most of the time it is not. So we want a vector that's always going to be orthogonal to big T. So how can we get that guy? So here's the idea. In example 2, that was the example we just did. Because you're in 3D, you can kind of think of infinitely many vectors that are orthogonal to the unit tangent vector. I mean, just take a look at this diagram over here. Let me try to, let me get rid of that. So if I draw a tangent vector here, here's your big T, because it's tangent to the curve. Let's see, I can draw a picture of a vector that's orthogonal to it, like pointing that way. And so it's making a 90-degree angle like that. Or heck, I can, kind of rotate it around. What if I wanted another vector to be orthogonal to the tangent vector, but pointing straight up? That would still be orthogonal. And I mean, I can rotate this all the way around, like pointing out this way also would give me a vector that's orthogonal to big T. So we have infinitely many choices, but we want one. And this is the trick. We want a special one. And we're going to call that, and it's going to end up being big T prime. So why is big T prime orthogonal to big T? I mean, are you always guaranteed of that? Because we just saw acceleration, you're not guaranteed. But the derivative of big T, you're guaranteed. It's a promise. My promise, yeah, that it'll be orthogonal to big T. So here's why. Let me show you the mini proof. I already proved, but I'll prove it again, that there was a theorem in a previous lecture that said if the dot product of a vector with itself gives you a scalar, a pure number, a constant, then here's what has to be true. The dot product of that vector with its own derivative will be 0. This was a theorem, and I did prove it, but I'll prove it again. So take a look at the premise. So you get this, say this fact is true. You get that for free because that's the premise. If you take the derivative of both sides of this equation with respect to time, I can't write today. The right-hand side is easy. Does anybody remember what the derivative of a constant is from Calc 1?
0.
Yes. And then on the right or the left-hand side, you'll use that theorem. It's a product rule that says the derivative of a dot product of two vectors is going to be r prime dot product with R plus, that's R, not R prime itself, plus R dot product with R prime. And then these are like terms, so you can add them together. So 1 apple plus 1 apple is 2 apples. And then divide both sides by 2, and voila, you have what the result is, okay? So what does this have to do with the unit tangent vector that we just defined? It has everything to do with it. So why is that? Well, take a look. You know that the magnitude of big T is equal to 1, right? Because that was the definition. We unitized it. So this is a fact. Yeah, that could be a good true false question, huh? Is true or false? Is the unit tangent vector's magnitude equal to 1? Haha, true by definition, because it's the unitized velocity vector. Okay, fine. And then we also learned from a previous theorem that, and I also proved this, that's basically said, and I don't know if you guys remember this one, but it is true. If you take the dot product of a vector with itself, it will give you the same thing as the magnitude squared. Do you recall this wonderful theorem from, I don't know, 2 weeks ago? Okay, so we're going to use that theorem in a moment too. So here's the deal. If you look at unit tangent vector dot product with itself, by this theorem right here, that is going to be equal to the unit tangent vector's magnitude squared. Okay, fine. But we already know that the unit tangent vector's magnitude is 1, and 1 squared is just 1. And this is indeed a constant. So what do we have? We have the dot product of the vector t with itself is equal to a constant. And so now we're going to use this theorem that says if you're lucky enough to have the dot product of a vector with itself equal to a constant, that doesn't always happen because it could be a function of time, then what you get for free is this fact has to be true, that big T dot product with his own personal derivative will be equal to 0. Voila. And that's why we're able to say this fact right here, that one of the infinite vectors that is orthogonal to big T, because there's infinity of them, is his own derivative, big T prime. Is that exciting or what? I love that. So what we're going to do is we're going to take big T prime and normalize it. Normalize is a fancy way of saying unitize. But unitize is not an official math term. That's what Dr. Malone taught me. So we're going to unitize big T prime, fill in that blank. And then you get a vector called the principal unit normal vector. Yep, the principal unit normal vector. And here's the official definition of the principal unit normal vector. Got a smooth curve? That means it doesn't have any breaks, sharp corners, cusps, holes, or any weirdness. And it's represented by R. That's a vector valued function. If your big T prime isn't the 0 vector, then big N, that's who we're defining right now, big N, principal unit normal vector, is the unitized big T prime. This is the unitized big T prime. Now, a lot of students wrongly think, oh, since big T is just the unitized velocity, oh, I bet this is just the unitized acceleration vector, right? No, it is not. So don't make that silly mistake. We just saw by that little animation that acceleration not always guaranteed to be orthogonal to the tangent vector. So you don't want to use that. That has nothing to do. You're going to find big T, take big T's derivative, then unitize that big T prime. So careful, I'm just going to write in the side margin here. Big N is not equal to the acceleration vector unitized. That's not going to help you get anything. If you go get that, you get no credit. Okay. Now, if you're in 2 dimensions, it's kind of easy to get big N. You don't have to do a whole bunch of algebra. You can kind of cheat if you're in 2D. Yeah, you can cheat. What do you mean? Well, after you get big T, which you know is a unit tangent vector, there's only 2 choices in 2 dimensions for an orthogonal vector. It could either point this way or this way. And you always want to choose your big N so that it's pointing in the direction the curve is turning. So this curve here, it's kind of turning, if I were driving in a car, a little bit to, cranking it a little bit to the left with my steering wheel. So the big N points to the left in the direction the curve is turning. Okay, so that would be your choice. So what we're saying here is the 2 cheating choices here would be negative y of t, x of t, because if you take the dot product of t and n, because remember you need t dot n equaling 0. That's another good true false question. Hey, is big T dot product with n always equal to 0? The answer to that is true. Absolutely. So this is one choice, or the other choice that would work would be, so you basically swap these components and take the negative of one of them. That's all they're saying. You choose the one that's turning in, pointing to the direction the curve is turning. So that's kind of cool. But in 3D, you don't get that trick because you have infinity vectors that are orthogonal to big T. So you don't get to do this cute little trick to circumvent finding big N. You have to do it the hard way. Find the derivative. Yeah. You have to be good at taking derivatives, you know, all that stuff. So in space, you cannot use that little trick. But we still have that the unit normal vector will point in the direction the object is turning. So they're showing you here if this curve is headed down this way, then this curve here is sort of turning, you know, driving along to the left. So the big N will point in the direction it's turning. Because you need big N to be orthogonal big T at all times. At all times, people, like for realsies. You don't get, some of the time. So the last little thing I want to cover here, and then we'll move on to another big topic, is something called the binormal vector. Binormal, oh my goodness, another vector. Now what? Well, big B, yeah. After you've gotten big T, and then you use big T to get big N, you have to do it in that order. If you take the cross product, you'll get a vector that's orthogonal to big T and big N, and we call him big B. That's how you get him. Yeah, and our physics brethren are very interested in all 3 of these vectors, okay? Because when you take them as a set, T, N, and B, they form a set of orthogonal vectors called the TNB frame. And the TNB frame plays an important role in the branch of math known as differential geometry. And it has applications to the motion of spacecrafts. If you're going to major in aerospace engineering, you might want to care about the TNB frame. And I got another cool animation for you. Yes, indeedy. I'm just full of fun and games today, man. Check this out. I want you to see the TNB frame here. You see those 3 vectors that always are orthogonal to each other? I think one of them is always tangent to the curve. One of them is T prime, and the other one, you know, that's a unit normal vector, and the other one's B. Isn't that cool? You guys all see the TNB frame as it moves around that curve, and they always maintain the relationship of being orthogonal to each other. Is anybody excited?
I am excited.
Yay! I hope you guys like this stuff. I mean, come on. It's fun. All right. Here's your TNB frame. Always moving around. Now, what we're going to look at the very end of this section is the plane that contains the t and the n vectors, that if you can kind of think of that as being flat, a flat plane containing those two vectors, the acceleration vector, you have a guarantee it will always live in the plane of t and n, which is kind of a cool fact in physics. Yeah, fun times, man. Okay. So let's do an example where we get big B. Not that hard. You guys have all the tools now. Oh yeah. So let's take a look here, and then we're going to do a sort of a little extra. It's kind of fun. We'll finish off by doing an equation of a plane. Yeah, that'll be fun because you guys know how to do that, and that's going to happen on the midterm too, finding equations of planes. Okay, so here's example 3. We're going to find big N, that's the principal unit normal vector, and big B, that's the binormal vector, for the curve from example 2 that we did already. That had this vector valued function r of t, 2 cos, 2 sine t. So remember when we did example 2, what was example 2? That was a long time ago, I forgot. So what we did in example 2 is we found big T, the unit tangent vector. Yay! So let's take a look at big T. And, you know, I know we evaluated it time equals pi fourths, but we're not going to use that answer. We're going to use the answer where we got big T as a function of time. So that was right here, right there. Okay. So we're going to take that and use that to go get big N and big B. Okay, so we're just continuing example 2 here where we already got big T. So I'll copy it down right here. So we already got that. Big T, the unit tangent vector, was this vector, negative 2 sine t over square root of 5, comma, 2 cos t over square root of 5, comma, 1 over square root of 5. Fine. Go get big N. Oh boy. Well, we know, what do we know? We know big N, by definition, is the unitized big T prime, the unitized big T prime. So in order to come up with big N, we got to do this step by step. Let's get big T prime first. That's not hard because, you know, that's just taking the derivative of big T component by component. Fine. Well, let's see. The first component, what's the derivative of negative 2 sine over square root of 5? And then the next component, what's the derivative of 2 cos over square root of 5? I think that's going to be negative 2 sine over square root of 5. And then finally, taking the derivative of that last component is a constant. Derivative of a constant is 0. Okay, there's big T prime. We're getting somewhere. All right, if we're going to have to unitize this, we definitely want to get the magnitude of it. So this is going to be a little messy. We're going to take the square root of the sum of the squares of the components. Okay, and it's nice because, you know, the square root is, or the square of 0 is just 0. That's convenient. I forgot to square that middle guy. Okay, and then clean this up a little bit. If you can clean it up. Sometimes it doesn't clean up well. But when you square 2 cos over square root of 5, you'll get 4 cos over 5. And then the next term after squaring is 4 sine over 5. And of course, squaring 0 doesn't get us anywhere. But then, and this should be squared. My apologies. Cos squared and sine squared. And if I factor out a common factor, which sometimes you can do if you're lucky, and we all know cos squared plus sine squared is a 1. So this is square root of 4/5, and I can even clean this up a little bit nicer because square root of 4 happens to be nice. So I get 2 divided by square root of 5. Okay, now what? Well, we're going to use that because big N, remember, is big T prime. I'm just going to copy big T prime over here. Divided by the magnitude of big T prime. And don't leave it like this, you know, clean it up, you know, reduce to lowest terms. And I think you can appreciate that after I distribute, when I divide by 2 over square root of 5 for all 3 of those components, we get some reducing to lowest terms. And so it looks real sweet now. It's just negative cos negative sign, and 0 for the components of big N. Ooh, convenient. Okay, so we're getting somewhere. There's big N. Now go get big B. The big B, the binormal, is the cross product of T and N. Now, I want to say something about some notation right now, because some of you, if you continue to do this, I'm going to take away points. Right now, I'm kind of being nice to you, but in the future, not so nice. I'll take away 1 point. When you're doing your 3x3 determinant, when you're finding a cross product, some things to keep in mind. I want these bars here on the side, that's the notation for determinant, to completely go all the way up. In other words, your top row, which is the unit vectors I hat, j hat, and k hat, they better be up there. This is what I saw some of you do. You went, oh, well, the I hat, j hat, k hat, they're not real. And my determinant, I'll have the bars come up, but not go all the way up. That's not any tradition. You're not going to see that in any calculus book. So that's why I'm not going to let you get away with it. Full credit, big old bars. Big old bars. Put them in there. And don't forget your I hat, j hat, and k hat. I want to see that, those little hats on there for notation. Okay, second row, I get the components of big T. So I got negative 2 over square root of 5 sine, and then 2 over square root of 5 cos, and then 1 over square root of 5. Bottom row, put the components of your unit normal vector, negative cos, negative sine, 0. And then you know the drill. You're going to have a 2 by 2 I hat minus a 2 by 2 j hat plus a 2 by 2 k hat. Please remember that the second term there has a minus in front of it. People kind of forgot on the quiz. And then, you know, you put in your stuff. So I'm going to sort of do this on the fly quickly. Kind of messy because I'm kind of in a hurry. Yeah. Don't do this at home, kids, where it's this messy. Yikes. And then our last 2 by 2. Yeah. Okay. So what are we getting here? Are we getting anywhere? Yeah, I think so. So if you're going to do the major diagonal, which is going to give you 0, minus the minor diagonal, you'll end up with, let me extend the page, positive 1 over square root of 5. That's, is that right? No, yeah, times sine. That's what it looks like. Yep. Yeah. Just make sure I have all this right. Yeah. So this first, I'm going to write this in component form. We're going to get sine t over square root of 5. Because the minus minus does a plus, and then the next term, I'll ignore the minus for now. You're going to have 0 minus a minus, that's going to be plus 1 over square root of 5 times cos, but then this minus that you see in front there is going to make the whole term negative. So do that. And then finally, you're going to have, oh my, this is going to be a mess. You're going to get 2 over square root of 5 sine squared minus, and then you're going to get minus 2 over square root of 5 cos squared for this k term, k hat. But then a minus minus is really a plus. And then once again, you have a common factor of 2 over square root of 5 that if you factor it out, you get the other factor of sine squared plus cos squared, but that's 1, yay. And then you see it just reduces to 2 over square root of 5. And we win. Here's the binormal vector. So this is big B. So we're almost ready to finish out this problem. Why? Because the final thing they wanted us to do after they said go find big N and big B, which we did already, good deal, we're going to find the equation for the plane that contains T and N. So if I draw a picture here, you know, let's say T was pointing this way, just say, and then we know N is always going to be orthogonal. Okay. And then we know that the binormal vector is obtained by taking the cross product of B and N. So it's going to be like pointing, say, that way, making a 90-degree angle with both N and T. Can you visualize here that the plane containing T and N has a normal vector, which we can use the binormal vector for the normal vector? So here's my claim to finish out this problem. This vector can be used as the normal vector to the plane. Containing T and N. Now, they did say they want to get the equation for the plane at time t equals 0. Okay, so we have some things we need to do. Okay, first, we want to get a point on the plane. Oh dear, how do we get a point on the plane? So the answer to that is you use your original curve, your position vector, r, and you evaluate it at 0 seconds. So the r of t, but if I substitute 0 for t, I get 2 cos 0, 2 sine 0, 0, and that will give you a point on the plane, and I get, 2, 0, 0. So there's a point on the plane. And now you need this binormal vector evaluated at time t equals 0 to get the actual normal vector to this plane. So you're going to go b evaluated at 0 seconds, and that's going to give me what? Sine 0 over square root of 5, but that's 0. A negative cos 0 over square root of 5, and 2 over square root of 5. That looks like it's going to be this constant vector. And so now you're ready for the standard equation. I know some of you haven't been using your standard equation because you go directly to general, but that I'm thrown to do the standard first. You go 0 times x minus 2, that's just going to be 0, plus, then you take your next component from your normal vector, negative 1 over square root of 5 times the quantity y minus, and then the position was 0, and then plus, next component, 2 over square root of 5, z minus coordinate of the point 0. That whole mess is equal to 0. We're almost done. 0 times anything, get rid of it. Distribute, so we're going to have negative 1 over square root of 5y plus 2 over square root of 5z equals 0. And I don't like fractions. Like plain equations that have fractions are legit, but they look yucky. So how about if we simply make this look pretty by multiplying both sides of the equation by square root of 5. Totally legal. And then we get our equation for the plane. This is known as the osculating plane, aka osculating plane. Okay? And that's the plane that contains both t and n at time t equals 0. Pretty cool.